All right, see you tomorrow, Jake.
All right, here.
Take some pizza.
Oh, thank
Have a
you.
bite now.
All right, everybody, welcome. Let's see. I see Brad is here, and we have David Mueller, who couldn't find us last week,
Oh
and Aiden and Tanya are here, and Wyatt is here, and Carson is here. So let's go back. Do we have Evan Hymas? Him. Alberto says he'll be late. Christopher Robinson, I don't see him. And then we also have Brennan, new guy as well. So welcome, Dave and Brennan. Thanks for coming. Alrighty. This is week 2, class 2, lesson 2, whatever you'd like to call it. We'll be talking about airplane systems, maintenance requirements, aircraft documents, weight and balance, and flying turns. Weight and balance is going to be the tough one. It's kind of a lot of boring talking about math, and I was a bad math student, so I don't know if I'll be a good math teacher. So we'll try. Alrighty. Systems, maintenance requirements, documents, weight and balance, and flying turn. Alright. Airplane systems. All these airplanes have a myriad of different systems. I mean, this looks like this is a 737 fuel system. These are all different valves and different plumbing to the 2 engines. I mean, it can be complicated stuff. Luckily, airplanes you're going to be flying are relatively simple. We've got oil systems, piston engines, and even jet turbine engines have different oil systems. Hydraulic systems for various accessories, electrical systems, we kind of covered on the flight controls last week. De-ice and ice prevention, which is not really a thing you need to worry about in general aviation. It's more for jets and altitude airplanes. And the ELT is the emergency locator transmitter that all airplanes have. So, fuel systems you might see on, I can't see with that. Fuel systems you might see on GA airplanes. Fuel pumps, we have mechanical pumps, like a lot of cars, and electric pumps. You might see fuel cross-feed valves. Fuel caps are actually kind of technical. Fuel quantity gauges, fuel pressure gauges, vents for the fuel system, carburetors and fuel injection systems. We watched that great video last week that talked a little bit about how the engine worked. That kind of touched on carburetors. So here's a complicated looking fuel system here. This is would be for a twin engine airplane. It's got 2 tanks on each side, and it's got 2 carburetors and 2 strainers and distributors and all that. But it's a map, and a lot of airplanes will have in their flight manual a map like this that shows you where a component is in the fuel system. And it's very important to know the fuel system in your airplane to prevent you from inadvertently selecting an empty fuel tank or selecting an off position on a fuel selector. 95% of airplane crashes are due to poor fuel management by the pilot. All right, so our Cessna 120, which is parked over on the other side, is the most simple fuel system you can get. And if you're going to be flying it with me, then we'll just go over that. Don't worry about all this stuff up here, but what we have here is we've got a left wing fuel tank and a right wing fuel tank. In each of those fuel tanks is a gauge. It's essentially a cork float. It floats on top of the gas and has a little mechanism that translates to a gauge on the fuel tank. Tells you how much gas we have. We'll look at the fuel gauge in a little bit. But then inside the fuel tank is a strainer. It's a very coarse screen that prevents junk that might be in the fuel tank from getting into the fuel line. Out of the bottom of a fuel tank you have a sump drain. Let's say you can take a sample of fuel. We do that to look for water that maybe got into the fuel tank or dirt and other contamination. water is a big one because airplanes don't run on water. And water is heavier than fuel, so the water will sink to the bottom of the fuel tank, and hopefully you can drain a little bit out of the fuel tank and catch it before it goes into the engine. And usually by the time you start the airplane up and taxi out, any water that got into the fuel tank has worked its way while you're taxiing and doing your run up, getting ready. And by the time you take off, it has finally made it to the engine. And then the engine quits working because it doesn't run on gas. So here we have a fuel selector. This is in the 120, this is down here on the floor between the pilots. You can select the left tank, the right tank. Some airplanes have a both selection, which means you're feeding from both fuel tanks. And the reason for that is you don't have to manage your fuel. You don't have to select one tank and worry about, did I fly? How much fuel is in that tank? You're just using all of the available fuel. Or an off position. The reason you'd select off in the case of our 120 is because fuel will begin to leak out of the carburetor if you leave it on, so we got to turn the gas off. But in most airplanes, it's so you can turn off fuel if there was a fire. If the engine catches fire, last thing you want to do is add more fuel to the fire, so you turn it off. After the fuel selector, we go to the gascolator. The gascolator is a little screen that picks up even more contamination. This screen here is very coarse. This is a much finer screen. And believe it or not, in your carburetor is another screen. We really don't want stuff getting in there. But coming off the gascolator is a primer, and that is used to put a little bit of fuel into the cylinders to help aid in starting. These airplanes, when they're sitting, there's no fuel in the carburetor, and it can take a lot of cranking on the starter to help draw fuel all the way through this fuel system into the carburetor to aid in starting. By then you've weakened the battery and you've been pretty hard on the starter. So the primer helps give us more fuel to aid in the starting. Let's see, on the 120, each tank's 12.5 gallons. Fuel selector allows the pilot to select the fuel source. Gascolator is the screen on the firewall. And the carburetor, we'll talk about a little bit more how that works a little bit later. Carburetors and fuel injection units work on a principle called PFM. Anyone know what that stands for? Pure effing magic. We're not going to talk about how they work. You just need to know what they are. Here is our fuel gauge indicator. So this is your range of fuel. This is your white or yellow line on your gauge, and this is your arrow pointer here. This little disc represents the fuel tank wall, and the fuel tank's over here. Here's a little float that floats in the gas, and as the level of gas comes up and down, it rotates that arm, which positions that arrow, tells you how much gas you have. It's so simple, but it works great. They still build them like that today, except for when you're flying around and the gas is bouncing around like that. You can imagine what that needle's doing, right? Going like that. So in Cessnas, we don't trust the fuel gauges. Before every flight, we'll take the gas cap off and we'll look inside. We'll put a stick down there and we'll measure our gas. Make sure we know how much gas is in the airplane and how much gas the airplane uses before we take off. Because you really can't rely on this.
Do you test the fuel for water also?
Yeah.
Before every flight?
Part of a pre-flight would be you check the fuel sample for water, that sump drain on the wings. Other airplanes have a sump down here on the firewall. So here's the drain on the fuel tank right here. At the back side, here's one. And then this is the gascolator. This is the screen before the carburetor. And there's a drain on it here too, so we check all those spots for water. The reason water gets into the tank, either condensation or it sits outside, it could rain and rain creeps its way in, or God forbid somebody opened it up and poured something in there. That stuff has happened, so we check all that stuff. Let's see, here's another fuel float. This would be an electric one. As you can see, there's a plastic little float here, and it moves that little arm, and this has got some electric doodads in it, and it sends out a signal to an electric gauge. R120 is very antique, so it doesn't have anything like that. Here's another one. This would be Some airplanes have a gas tank like this one right in the front of that cockpit there. You can actually look at one of those knobs there for that front windshield, and that's a fuel gauge. It works like this. Imagine this is the top of the airplane there in front of the windscreen, and the pilot is looking this way. That's a little glass screen, but here's your float that's down in the tank, and it runs that little rod and gives you a display on the little screen there. Or this one, like the 120, is in the fuel tanks that are in the wings. When you're sitting in the pilot seat, you look up at the base of the wing root, you can see the face of a fuel gauge there. Fuel pumps. We've got electric and mechanical fuel pumps in general aviation airplanes. The electric fuel pump can sometimes be known as a secondary pump or a boost pump. That will be commonly seen in an airplane where the fuel source is level with the engine or below the engine. So this airplane has the fuel up high in the wings, and it relies on gravity to feed the fuel to the engine. But an airplane like a Cherokee with a low wing doesn't have enough gravity pressure to feed that. So the primary pump on that is a mechanical pump attached to the engine, and we utilize an electric pump as a boost pump to aid in starting, kind of like the primer, and for items like taking off with a low fuel quantity in the tanks. We don't want air to cavitate with the sloshing fuel, so the electric pump makes sure it keeps positive pressure on the fuel system to keep the airplane running. Mechanical fuel pump, these are supposed to be animated, but this would be a mechanical pump attached to the engine. The engine pushes this dark red valve down. This yellow arc here is a diaphragm, and it pushes down and retracts. And just like principles of an engine, as it pushes down, that little valve, you can see, would come open, and it would push the fuel out that way. And then as the diaphragm's pulled up, now it sucks fuel in this way, fills that chamber until it pushes down again. As it pushes down, the pressure closes that valve, and that valve opens, and cycle is kind of continuous. There's a different style pump. You can see the fuel comes in here. As it comes down into this area here, it's getting compressed. It's a larger volume here than it is here. And these little veins kind of stick out, grabs a wad of fuel there, and as it comes around here, it compresses that volume. And I think that's the outlet there. Ignore that stuff. There's a number of different pump designs, and you don't need to know too much how they work, just that they are called positive displacement pumps because they move fluid one way. This is what a fuel primer would look like. You won't see this part because this is on the instrument panel, so you'll just see this part. Just a little knob that you pull out, and you can push it back in. You'll feel the fuel getting sucked up one way, and as you push it, pushes the fuel into the engine. Depends on how many times you're going to pump that little primer, depending on each type of airplane. Fuel crossfeed is a big airplane thing. That's where you usually have 2 or more engines, and you have multiple fuel tanks in each wing. You might have fuel tanks in the fuselage. And if you lost one engine in an airplane, the other engine is going to need more power to keep flying, therefore it's going to need more gas. And you might need to move, if the left engine quits, you might need to move left engine gas over to the right engine to finish getting across the ocean on your way to Hawaii or something. But you're not going to see that in general aviation airplanes, but it is a thing to be aware of because it is on the test. Fuel caps. Vented caps versus unvented caps. Most airplanes, like our 120 and our Pacer, don't have a fuel pump on them. They don't have a mechanical pump, and they don't have an electric pump. That's because the carburetor relies on gravity to supply it with fuel. The high wing on the airplane elevates the fuel supply above the carburetor, and gravity delivers it to the carburetor. If the tank was sealed, imagine a sealed water bottle. And as you pulled you you sucked all the water out of it, this thing's gonna start to crush, right? You've seen that with altitude changes on bottles. It needs a vent. You poke a hole in it, you hear it hiss, and then the bottle takes its shape again. You can imagine at some point it would be real hard to keep sucking the water out of that thing if you didn't vent it. Well, the same is true for the fuel system on the airplane. There needs to be a vent in there, so as you draw fuel out of the fuel tank, air needs to displace and take up that same volume of space that fuel was previously in. So we vent it either by a vent system or a vented fuel cap. If you have a airplane that doesn't have a fuel vent system and relies on a fuel cap, and for whatever reason you put a wrong fuel cap on it, an airplane will quit running. You'll have plenty of gas on it. The Cessna 120 has specific directional vents, and I'll show that. The Piper Pacer has doesn't have vented fuel caps because it has a vented fuel system. And if we fly that airplane, I'll show you where it is. Here is our 120 fuel cap. So that is forward on the airplane. See that little scoop on it? That's so when air's coming over the wing, goes in that fuel tank, it actually pressurizes the tank a little bit. That actually helps push some of that gas into the engine. But if you put that on backwards, and it would physically go on backwards, then you've got the scoop on the backside, and you've got low pressure on top of the wing making lift. That low pressure can actually start sucking fuel out of your fuel tank. Ask me how I know that. Let's see if we can't play this video. Oh, this is not gonna work. All right, well that's not gonna work. All right, that's not that important. Except I have multiple of them. I'm not a technology person, so this took all day for me to figure out how to do this. I'm still not getting it.
It'll get easier.
I'll figure it out by week 8.
You need to get one of these kids involved, I think.
No, just put Aiden on it. No, that's not it. Let me go to the next one.
Even some kids are bad at ground too.
Is it up? Can you see it?
It's back on the.
Yeah, on the home screen. What are you doing? Something. Yeah.
There it goes.
Did you fly? Yeah.
All right. Is this one next already? Here is a fuel injection system. Here we've got our engine. This will be the top of the engine looking down. We start with our fuel tank over there, is our fuel source. We have the auxiliary pump or the boost pump. That's the electric pump. Here's our engine-driven mechanical pump. And that, between the two of those, draws the fuel into the fuel metering servo, or fuel injection unit or carburetor. You can see how the fuel there could bypass this auxiliary pump. So you can either use it or not, and fuel will still get to the engine-driven pump. If this pump failed for whatever reason, you can use the electric auxiliary pump, and you still get fuel pressure because of that secondary pump. Here's our fuel controller. We've got a lot of different names. Fuel injection we call it fuel servo, fuel control unit, fuel injection. It's all one and the same. Fuel comes out of it, goes to a distributor valve on top of the engine. And here it takes this one source of fuel and divides it into whatever the number of cylinders are on the engine. So in this case, here's a 4-cylinder engine, and it splits up that fuel flow, and it directs and takes the fuel source and injects it right into the combustion chamber. And it's a relatively simple system. unlike the carburetor, where the carburetor is mixing air and fuel together, this one's just putting fuel directly into the cylinder. But this is what's affects how much fuel is going into the engine. This lever is going to be connected to your control in the cockpit, and that's how you control how much fuel is going into the engine. Your lever in the cockpit will also meter how much air is going into the engine, because it takes air and fuel to have combustion in the engine. This does meter both, but right now they're separate. Air is actually coming through this into the engine, and fuel is separate. They're actually almost two very distinct systems on a fuel injection unit. That's what one looks like. This is a little mechanical for you guys. You don't really need it, but there's fuel in, and then there's fuel out. Air comes in through here, into the engine through that. This is where we can adjust idle and adjust fuel mixture settings and stuff. Here is a carburetor. They're kind of similar looking. One thing you'll notice about the fuel injection unit is the air is coming this way. It's what's called updraft induction, and that's because the air is going up. The reason for that is because if you look at this airplane here, here's our carburetor. Here's the air that comes in. Then it goes up and it gets distributed into the engine via these tubes here, so that draft is up. Carburetors on cars are downdraft. Carburetors on top, and it goes down. So it won't work on a car. But the carburetors are the same. Draft comes in from the bottom, goes out the top. Here is a cutaway of a basic carburetor. This is the float bowl, and here's your float. And essentially, what happens is, when this float is at a predetermined spot, usually about half full like this, the carburetor knows it's getting enough fuel. If it starts needing more fuel because the pilot asked for more fuel, the float would sink, and more fuel would come into the carburetor bowl. Once it comes down here into the venturi, here's your updraft air coming in, and it helps draw the fuel up into the engine. And here the fuel is mixing with the air, and then the volume of the fuel air mixture is metered with this butterfly valve. You meter the amount of fuel that's going into the carburetor by what's called the mixture control, and that effectively meters the fuel going into the bowl and how it goes into the carburetor.
There's actually a cool YouTube video on the carburetor. They printed it out of plastic, and it shows exactly how the Venturi effect comes.
Oh yeah,
fuel.
there's so much of the stuff that you can study, but for your private pilot license, basics on this is good enough.
So is it a pretty dynamic process while you're flying them when you have a carburetor on the plane for the fuel air mixture because of the change in temperature and
The
speed?
pilot still has control over air and fuel in both a carbureted and a fuel injected airplane. You just treat them a little bit different, but they're not so much different that if you've been training in a carbureted airplane, you jump to a fuel injection airplane, it would still mostly work okay. Some people actually don't know they're flying a fuel injected airplane until somebody points out, hey, you're leaning the airplane wrong. It's not difficult to do. It's one more step that when you're flying, but adjusting the fuel and air mixture is not something you do when takeoff. When you ask for takeoff, you're going full power with full rich mixture. You're asking the carburetor to give the engine as much fuel as it'll give it. And then when you go open the throttle, you're opening this valve here. This is the throttle valve. You're giving as much of that air-fuel mixture as possible for maximum power. You don't need to worry about what the mixture setting is. The mechanics set up the mixture setting ahead of time, so it should be okay. When we do our run-up checks, one thing we're checking is that that mixture is correct. And so we bring the power up, We'll lean the mixture a little bit and look for ideal RPM. And that's what tells us that the airplane is set up correctly.
That's a run-up check, something that mechanics do.
So mechanics do it, but when you start up the airplane and taxi out, before you take off, you're going to do a run-up check. You're going to go through every system on the airplane and make sure it works before you take off. So one thing we do is we run the engine up. Not really full power, but high power setting. Make sure the airplane engine's not going bang, 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 and running wrong. We want to make sure everything's working good. And we'll check out the 2 magneto systems. We'll check out the fuel air mixture. We're going to check to make sure it's making good power. No weird noises or vibrations. We're making sure the oil pressure looks good and the temperatures look good. There's a lot of things to check. You know, when we looked at that instrument panel with all those gauges on it, there's a lot of things to check on that. But something like this airplane or R120, there's only a few engine gauges to check. And you're mostly hearing and feeling it in your butt, you know, with weird vibrations and stuff.
And is that something to just develop over time?
Yeah. I mean, we'll go over, each airplane is very different. You know, this airplane, you might go, oh, this one's a million times more smooth than the 120, and that might be normal that way. Okay, oil systems on both reciprocating piston engines and turbine engines. You're going to have an oil pump somewhere. Again, this is supposed to be animated, but just like the fuel pump, here's what an oil pump looks like. Oil comes in this way. This driving gear is run off the engine, and it's a gear runs against the driven gear there, and it pushes oil up around and out the top. And the design of that makes the oil come out at a certain pressure that's optimum for lubricating internal engine parts. Here is our engine again, but this time we're looking at the oil system. So you'll have somewhere on the airplane, you're gonna have the oil filler, well that's its filter, but you're gonna have the oil filler and dipstick. That engine is on the right side, R120, there's a tank at the bottom, and so you go from the top, there's a nice long tube that goes down the tank, and you pull out the dipstick just like your car and make sure there's enough oil. On the bottom of the engine is the oil sump. That's kind of hard to see on this engine because it's hidden by stuff, but this is your oil sump down here. This is like the oil pan on the car, and the induction system actually goes through that. It's not mixing air and oil. There's a passageway in there, but that's what holds all the oil. You have an oil pressure relief valve. What that does is, if oil pressure gets too high because there's a blockage somewhere, it can open up and relieve that oil pressure and bypass the plugged condition in the engine. We've got a oil pressure, oil pickup screen in the bottom. The bottom of that sump, there is just a very coarse screen with a tube in it, and the oil pump is sucking oil out of that sump into that tube, and that's what goes into the system. So, comes up through the coarse screen there to make sure no things like rags or big bugs get in it. Comes here into the oil pump. Now it's pressurized. It's going to go through a screen, maybe a filter that looks like an automotive filter. Some airplanes, you might have a temperature, or you'll certainly have a pressure gauge. You can have both. You can have temperature and pressure gauges. And then it goes into the engine, and it feeds different parts of the engine in here. Goes up into the cylinders, and when it's all gone through all the different ports inside the engine, it'll terminate inside that sump again and mix with cooler oil, bring the temperature of the oil down, and hopefully cool off enough to be good for the next cycle that demands that oil. Sometimes in this system you'll even see an oil cooler. Higher horsepower, higher performance airplanes will have an oil cooler on the front that works like a radiator to exchange the heat for the cool air. They pump it through little tiny veins, and it's a little grate, so air passes through it, helps bring the temperature of that oil down, and that oil, cooler oil, can return to the engine. Other oil systems, we'll talk about constant speed propellers in a little bit. but constant speed propellers are actually actuated by engine oil, but they're considered a hydraulic system. Propellers. We have, oh, that's missing. First you have fixed pitch propellers. A fixed pitch propeller is not adjustable in any way. It is designed the way it's designed, and there's nothing you can do about it. Let's grab a propeller. Let's scratch it up. Here, fixed pitch propeller. It's a big chunk of metal. You see it's not moving, right? So that'll be the front of the airplane. You see how it has more blade angle here than up here? Anybody have a guess as to why that is?
Going faster at the tip.
Exactly. Right? Last week we talked about angle of attack. This tip is going faster than this part of the blade, so that's why it needs less angle of attack. That's also why it's smaller and thinner and all that stuff. So that's designed the way it is to be as efficient as a fixed pitch propeller can be. You can't have different angles on those blades. A coarser pitch, which would look maybe more like a boat propeller, a lot of angle, more like a 45-degree angle, would be for a faster speed, where a fine pitch and less angle is for more climb. Picture a propeller, if you will. I tried to find this video, and you put it in Jello, and you turned it one revolution. How far forward would it go? If it had more angle or less angle in one turn, it would go farther, right? The air is the same. It flies through the air just the same as it would a liquid. And so that's why that's designed the way it is. This propeller is a happy medium between most angle and less angle, because we want it to go kind of fast and we want it to kind of climb good. A constant speed propeller, though, has adjustable blades, and the pilot can adjust them to achieve optimal propeller efficiency. The reason would be you want the propeller to climb better when you're taking off, and you want it to go faster when you're cruising, right? That propeller, we can either choose to climb or we can choose to go fast. And I do, I've got two propellers for that airplane. If I'm going to Idaho, I'll put a fast propeller on it. If I'm going around there, it's a hot summer day, I'll climb, I'll put a climb propeller on it. But the constant speed, which is what this propeller is, and if you actually look at it, you can see that it's got a mechanism in the center of the hub of the propeller there that allows the blades to move. And we have a video for that. So. Oh!
We'll now examine a fixed pitch propeller. The type of propeller fitted to the majority of small single-engine light aircraft. As its name suggests, the blade angle cannot be changed. There are two types of fixed pitch propeller, the first of which is the cruise propeller. A cruise propeller has a large blade angle to give maximum efficiency at the cruising speed of the aircraft. A large blade angle is called coarse pitch. The other type of fixed pitch propeller is called a climb propeller. This type of propeller is not very common. To give maximum efficiency at low speed, a climb propeller has a smaller blade angle than a cruise propeller. As an example, an aircraft used exclusively for glider towing would be fitted with a climb propeller. A small blade angle is called fine pitch. So that we can see some of the factors that affect the efficiency of a fixed pitch propeller, we have replaced the plane of rotation with a vector of propeller RPM. A propeller fitted to the piston engine of most light aircraft will rotate at the same speed as the engine. We've now added a speed vector that represents the true airspeed of the aircraft. The product of the propeller RPM and the aircraft true airspeed is the relative airflow. As with any aerofoil, the angle between the chord line of the blade and the relative airflow is the angle of attack. In this case, the blade angle of attack. We will now vary the engine RPM to see how the blade angle of attack is affected. 2300 is a typical cruise RPM. As the engine RPM is increased, the angle of attack of the blade increases. For simplicity, we have maintained the same true airspeed, although in practice it will begin to increase. Decreasing the RPM decreases the blade angle of attack. Let's now consider the effect of aircraft true airspeed on the angle of attack of a fixed pitch propeller. At low forward speed, the angle of attack is very big. The illustration shows a typical light aircraft just after brake release on the takeoff run. One of the disadvantages of a fixed pitch propeller is its lack of efficiency at low forward speed due to the large blade angle of attack. You could think of it as the propeller trying to accelerate too much air rearwards for the power output of the engine. We'll now see what happens as speed is increased to the cruise speed. Watch. The angle of attack decreases as the true airspeed increases. Now the angle of attack is optimum for maximum efficiency in the cruise. You could think of it as the propeller being able to accelerate just the right amount of air rearwards for the engine power output. If we look again at the fixed pitch climb propeller, you can see that it has maximum efficiency at low flight speed. We'll now take a look at the forces of thrust and torque and how they act on the aircraft. Here, we can see a propeller blade with its angle of attack and the plane of rotation. Thrust acts forwards at right angles to the plane of rotation, and torque acts parallel to and in the opposite direction to propeller rotation. Torque is the equal and opposite reaction to the propeller being rotated by the engine. We will see later that torque will generate a yawing moment about the aircraft CG. Next, we'll take a look at propeller efficiency. The illustration shows a plot of the efficiency of a fixed pitch propeller, with aircraft true airspeed increasing to the right. It's a standard cruise propeller, the type fitted to the majority of small single-engine light aircraft. You can see that peak efficiency occurs at the cruise speed of the aircraft. It makes most sense to use a fixed-pitch cruise propeller, as most aircraft spend most of their flight time in the cruise. Unfortunately, a fixed-pitch cruise propeller is not very efficient at takeoff speed or climb speed, so use of a fixed-pitch cruise propeller is a compromise. In comparison, a fixed-pitch climb propeller gives maximum efficiency at low speed, but unfortunately is totally unsuitable for flight at a sensible cruising speed. For optimum efficiency across the required speed range, a propeller whose blade angle can be varied in flight is required. Fine pitch for takeoff and climb, and coarse pitch for cruising. This type of propeller is called a variable pitch propeller. The plot shows a variable pitch propeller at low speed with the blades on the fine pitch stop. This will give maximum efficiency during the initial takeoff run. And as speed increases, the efficiency increases. The increase in efficiency with increasing speed is due to the blade angle progressively increasing to maintain the optimum angle of attack. Therefore, a variable pitch propeller will give optimum efficiency and performance throughout the aircraft's operating speed range. The mechanism that changes the blade angle in flight was fully explained during your study of piston engines and will not be repeated here. The variable pitch propeller will be discussed in detail in the next lesson.
All right, so for you two guys that weren't here last week, we talked about angle of attack. It's pretty important to that lesson there. And I know it's clear as mud, right? How many of you drive a stick shift? Right? Okay. You know when you're at a stop and you put it in third gear and try to accelerate? That is what a fixed pitch propeller is. It's your automatic transmission, whereas the fixed pitch propeller is trying to take off in third gear, because you want to be able to go, if you had to pick one gear and you wanted to go from a stop and accelerate forward and go on the highway, you put it in third gear probably, right? But well, it still doesn't work very good for either of them. And that's the bane of the fixed pitch propeller. So the physics of the propeller is it's complicated stuff, and that might have been a little complicated in the video there, but essentially by changing the pitch of the blade, you can adjust the angle of attack on the propeller, and it becomes more efficient.
When you change your propeller, you know, for speed, what's the difference you see in speed?
It'd be tough for me to say, because an airplane like this was designed with this propeller. This airplane was not designed for a constant speed propeller. So this airframe, if you theoretically just put one on the front, how much faster could it go?
Can you tell more of the sound of the RPMs of the engine and the way it's working? More or less?
The airframe is a limiting factor on speed. I mean, this thing probably couldn't go too much faster. But the constant speed, here they call it variable pitch propeller. Constant speed is one and the same, because by changing the pitch of the propeller blade, you're maintaining the same RPM. In a fixed pitch propeller airplane, you have one power gauge, and that's your tachometer, your RPM. But when you get into a constant speed propeller, the RPM gauge becomes the speed of the propeller, and power output is displayed on a different gauge called a manifold pressure gauge. That's how much the engine is sucking and how much air is flowing through the induction system. So to say how much faster you get out of a constant speed is tough to say, because it's dependent on what kind of airframe it's on. But you know, if theoretically I could put that propeller on this airplane, it'd probably go 10 miles an hour faster. There is one of these out there that's got one on it. The trade-off is all of a sudden now that propeller weighs 27 something pounds, or no, that weighs 47 pounds, that weighs 20 pounds. So you got 27 pound difference in weight at the nose, and that puts the airplane out of its weight and balance range, which we'll talk about soon. So you have to put a bunch of weight in the tail. So all of a sudden you added a bunch of weight to the airplane to make it go a little faster. Well, the weight is more weight. Weight makes less lift. You need more thrust to go. You know, I mean, it's not really it's not a one-for-one trade-off kind of thing.
On the constant speed, are you controlling that pitch manually?
Yeah.
Yeah, okay.
Yeah, there's it's known as the blue knob.
Yeah.
You'll see in some airplanes. But you set it to where you want. You know,
Yeah.
a lot of these manuals in the airplane will have a power setting. It'll say, you know, we want 24 inches of manifold pressure and 2,400 RPM. So you take your manifold pressure gauge, you push the power up till you get 24 inches manifold pressure on that gauge, and you push your prop lever till you get 2,400 RPM. It's set the power. It's really not complicated at all.
Yeah.
Knowing what power setting you need is the harder part. Each airplane is a little different, and you could fly 2 or 3 of the same exact airplane, different owners, and say, I like this power setting. There are efficiency things, but some guys go, 2,400 RPM is too hard on my airplane. That's wrong, but if you're flying his airplane, you do what he says, you know. So here is a constant speed propeller, and don't worry if this doesn't make any sense, because this is just, we're just gonna cruise through this because you don't really need to know much about this. But essentially, here's your propeller blade sticking out. You've got a hub coming off of it. That's the crankshaft of the engine up there. So you've got high pressure oil that comes through a hole in the crankshaft. And that oil that comes through the crankshaft is metered by something called the propeller governor. Then a piston inside the hub here is connected to each blade. And so as the governor meters the amount of oil pressure, the more oil pressure that pushes on that piston will change the angle of those blades. Some airplanes will have a nitrogen charge in the front of the hub to assist in changing the pitch. That kind of stuff is usually on a twin engine airplane, where when you're doing training in a twin engine airplane, flying a two engine airplane is about flying on one engine. That's what twin engine training is. What happens when the engine quits. So a lot of those propellers, so they're not sticking out there shut down making drag, they'll actually, what they do is called feather, where they go parallel with the airflow to make less drag. And when you don't have an engine running to make oil pressure, you don't have a way to move that propeller. So they put nitrogen in them to help move. But that's not something you'll see until you get into advanced airplanes. All right, this one a little shorter.
Most training aeroplanes have a fixed pitch propeller that is designed to operate most efficiently only at one particular airspeed and engine RPM combination. The propeller blade has the optimum angle of attack at this airspeed. However, as the airspeed increases, the angle of attack becomes smaller than optimum, and as the airspeed decreases, the angle of attack becomes greater than optimum. The variable pitch propeller was developed to address this problem. Its blade angle can be changed from fine to coarse, or any position in between. On modern aeroplanes, this is known as a constant speed propeller. It allows the propeller blade to maintain the optimum angle of attack as the airspeed increases and decreases. The blade angle changing mechanism is operated hydraulically with help from a device called the governor. The governor is driven by the engine crankshaft and consists of rotating flyweights. The governor forms part of what's called the constant speed unit. The governor flyweights are engine RPM sensitive. So as the engine RPM increases, the centrifugal force moves the flyweights outwards, and as the engine RPM decreases, the flyweights move inwards. The pilot can control how much the flyweights move through a blue lever called the propeller pitch control. This lever sets tension in a spring attached to the flyweights. It allows the pilot to request a target RPM which the constant speed unit will automatically try to keep constant in flight. The governor flyweights are connected to the pilot valve. This valve acts like a gate that directs oil to or from the propeller hub, which in turn sets the required propeller blade angle. Let's have a look at a couple of examples of how the constant speed unit works. This is a step-by-step breakdown of a process which happens quickly, continuously, and automatically. With the propeller pitch control set back, the pilot requests a lower target RPM. But if the aeroplane pitches down, for example, the propeller wants to speed up. Thus, the RPM wants to increase. The flyweights move outwards, open up the pilot valve, and allow oil to flow into the propeller hub. The blade angle increases so that the propeller takes a bigger bite of the air. This requires more engine torque, so the RPM slows down and the fly weights move back to their equilibrium position. The pilot valve closes and the blade angle and engine RPM is maintained. With the propeller pitch control set forward, the pilot requests a higher target RPM. But if the aeroplane pitches up, for example, the propeller wants to slow down, thus the RPM wants to decrease. The fly weights move inwards, open up the pilot valve, and allow oil to flow out of the propeller hub. The blade angle decreases so that the propeller takes a smaller bite of the air. This requires less engine torque, so the RPM speeds up and the fly weights move back to their equilibrium position. The pilot valve closes and the blade angle and engine RPM is maintained. The main benefit of the variable pitch propeller is that it provides peak performance at every phase of flight, from takeoff to landing. The pilot can select the RPM that provides the most suitable power for any situation. This improves fuel efficiency and reduces strain on the engine.
All right, makes a ton of sense, right? I would say that's a little bit more than you need to know. And in your private pilot training, there's a good chance you're not going to fly an airplane with a constant speed propeller. That's a lot less common. Springfield has that 172 RG. They use that for commercial training because you need, for the commercial requirements, you have to use a constant speed propeller and you have to do retractable gear. But up until then, it's an expensive part to have on an airplane that's used for training. So you really won't see that too much. But it is stuff that they do ask a little bit about on your written tests. So. Here's just a drawing again. Here, a governor would sometimes be on the front of an engine like this. You look in one of the air holes on the cowl and you would see the governor. It's kind of cylindrical shaped like that. And it's taken internal plumbing from the engine for its oil pressure. It spits it out the crankshaft. We talked about the twin engine airplanes where you might have an accumulator for nitrogen for feather position if the engine was stopped, but that's a multi-engine thing, so you don't really need to worry about that too much. All right, hydraulic systems. Let's see if I can make this one play now. Unless anybody's got questions about propellers.
Okay, in this video we're talking about the hydraulic system in this airplane.
Do I sound like that?
System 120. This airplane only has one hydraulic system, and that's the brakes. Each wheel has its own brake, and that is used to help assist steering, keeping the airplane straight on the ground. Here is the pilot side pedals, and you can see behind each pedal, here is a brake master cylinder, and there is a brake master cylinder. These are both reservoirs that hold hydraulic fluid. When your toe brake is pushed forward, that pushes that shaft into your reservoir, pushing hydraulic fluid down through the reservoir into a hose that goes through the bottom of the airplane, exits the airplane, comes here down the length of the gear leg, and into the brake caliper. When the hydraulic fluid is pressed, that pushes a piston inside of the caliper against this plate, and that's a brake line, and here's our brake rotor. Pushes the lining against the brake rotor. The brake rotor is attached to the wheel. It puts the drag against this rotor. It helps
Gosh, it's windy that day.
we're holding stock.
So, the theory how brakes work is all you fellas I know about brakes and cars and stuff, but all you're using is the hydraulic pressure on the cylinder to drag against that system. But this airplane only has one hydraulic system. That's the hydraulic system. We don't have hydraulics running flaps. We don't have hydraulics opening a door.
Hydraulic systems actuate flaps.
That's it.
Airplane.
All keepers.
Okay,
Okay,
this
just
video
talk
we're
what you want.
talking about
Shut up.
hy-
Other hydraulic systems. You might see flaps, brakes, constant speed propellers. They used oil, engine oil, but it's still considered a hydraulic system. Because does anybody know what hydraulic means? Come on.
Fluid.
That's what it sounds like.
Yeah.
Fluid, right? They mined all the dirt from the rocks away. It was called hydraulic mining. They compressed a bunch of water and blasted the rocks away with it. Hydraulic, I'm sure it's Latin for hydro, water. You also see retractable landing gear, and some airplanes have a thing called oleo gear. It's almost like suspension for the landing gear, and it's a hydraulic cylinder.
Nearly all airplanes are equipped with a hydraulic system. While small general aviation airplanes may have small, simple hydraulic systems, bigger jets have very complex hydraulic systems. In smaller airplanes, the hydraulic system powers the brakes to stop the airplane, extend and retract the landing gear, and change the blade angle on some constant speed propellers, as previously discussed. On larger airplanes, like those used by the airlines, the hydraulic system powers a majority of the airplane, including the flight controls and flaps. Usually, a hydraulic system consists of a reservoir where the hydraulic fluid is stored, a pump that moves the fluid, a filter to keep contaminants out of the system, a relief valve in case of a hydraulic malfunction, and actuators which the hydraulic system operates. The hydraulic system works by pumping incompressible fluid through hydraulic lines from one actuator into another, causing the actuator pistons to extend or contract. The hydraulic pressure exerted throughout the actuators is significant, making hydraulic systems very powerful. Let's examine the brake system on a typical general aviation airplane. As the pilot presses on the brakes, a piston drives fluid from the brake actuator on the pedal through hydraulic lines and then to the actuator near the wheels. The fluid pushes a piston, which then mechanically squeezes the brake pads against the brake disc, causing the airplane to slow down.
I couldn't have said it better myself. One thing I did catch in my fifth viewing of this was he said incompressible fluid, and that's why hydraulic systems are used. Water, oil, it's not compressible. So when you pump that much fluid that way, all of it's going that way, short of there being a leak, and that does make them very powerful. Hydraulic system, just like the engine oil system, it's got pumps, it's got check valve, pressure relief valves, filters. A fluid system is going to have all those kinds of things. But pretty much brakes is all you'll see hydraulic system on an airplane. It is a red fluid, and sometimes you could, if you're flying an airplane, come up and there'd be a pile of red fluid under your wheels. It means your brakes probably aren't going to work, and you need to fix them. All right, electrical systems, 120. The 120 is a great airplane for training here because it has the most rudimentary systems.
Okay, we're talking about the electrical system in our Cessna 120. In this Cessna 120, our battery is kept behind this bulkhead pan. And if you're going to be flying the airplane, it's good to know where this stuff is. Here's the battery box. Secured with pins on either side. I've already removed that left side pin.
You're not going to be opening the box on
Here is the battery. This is a 12 volt flooded lead acid battery in probably by the time you see this, probably have replaced this battery.
That battery's not in the airplane one. I filmed that a week ago.
What we have on the right side there is the ground strap that grounds to the airframe. On the left side is the positive terminal. And it goes to the solenoid that is attached to the back of this battery box. That is your master switch solenoid. When we flip the master switch on, now look at that.
I left it on.
That master switch was left in the on position.
So that's why that battery's not in there anymore.
Up is off. Switches were left.
Most airplanes, switches up is on. That's a pretty standard thing.
Replacing that.
This is 1946, was before they standardized it. And that's why I leave them on all
When
the
you
time.
flip this master
I
switch
turn them
on,
down, which should normally be off.
That
So if you fly my airplane, make sure you do that right. Otherwise, I got charged $50.
Now, there's not a lot of electrical equipment installed in this airplane. There's a generator mounted to the engine. There are nav lights. Down is on and up is off. This also says landing lights, but this airplane is not equipped with landing lights. We have a Hobbs meter that would be running when the master switch is on. And we have added a USB power supply here for convenience of pilots with iPhones and
Most high-tech thing on the planet.
Yeah.
this airplane
Cheapest
also
part of
has
the plane, too.
a handheld radio that normally mounts here, and this pilot intercom system. However, these are both battery powered. This intercom is 9-volt powered, and the handheld radio that sticks here is powered by its own battery. These are
Here's the radio for that
indicative
airplane.
of the aircraft's electrical system. The magnetos that are used for ignition on the engine are also independent of the electrical system. Not only in this airplane, but all airplanes. The idea is the magnetos are independent of the electrical system in case there's an electrical failure. So the only things we have electrical on this airplane, we have the generator that would charge the battery. We have our nav lights. We have our electric Hobbs meter. We have our USB power port there. And we have an amp gauge that shows the output of the generator. Other than that, there are no electrical systems.
I missed one.
in this
Anybody know what I
airplane.
missed?
This is a very rudimentary
It's like you know what you're talking about.
aircraft with rudimentary systems. Here is our generator, right down here.
Pretty simple looking.
This
There's
is
two wires
the
coming out.
regulator.
It's not that complicated kind of stuff.
It controls how much voltage and amperage is grounded to the airplane, because the generator only makes one output. Alternators run quite a bit differently. For the sake of you, the private pilot applicant, the differences between generators and alternators are not important. This is one of the mags, this is magneto parts. There's nothing else under here that runs the electrical system on this airplane. She is a very simple
Except starter, right?
electrical system. On to the next system.
All right.
Why do you have a generator switch? Seems like it would just be on, you know?
Yeah, good question. I guess the main reason for the generator switch is if there was an issue with the generator, it is fire potential if there's a
Overcharging or
problem,
something, yeah.
overcharging or something like that.
That's
That's actually a good question. I don't really actually know the answer to that.
Sense.
It's pretty common. It's so if that's what that actually controls is the field on the generator circuit. So if the the generator needs to spin at a certain RPM to make its magnetic field and start making electricity. If you had a weak start because internal parts are worn out or something, it might not actually output. So if you started it, you had a weak output, you could turn the field back up, ground the field out, turn it back on. Now that it's spinning, it would re-energize.
Okay.
That's probably not the right way to say that, but
Yeah, get you.
but good question. I will do more homework on that. I should know that. I don't rebuild them. I just install them.
What year is the 120?
1946.
Cool.
Yeah, right?
Mm-hmm.
Oh, come on.
Okay, we're talking about the electrical.
Gosh.
The electrical system provides electrical power to many different systems, from some flight instruments to aircraft lights to flaps and landing gear. The electrical system powers them all. The electrical system is usually comprised of a 14-volt or 28-volt direct current or DC system, made up of some basic components. These consist of an alternator, a battery, switches, circuit breakers or fuses, relays, a voltage regulator, an ammeter or load meter, and the electrical wiring which connects it all. Let's study some of these components in more detail. Similar to a car, the alternator is driven by the engine through an alternator belt, which generates electricity for the entire system. The alternator is the primary means of powering the electrical system during normal operations with the engine running. Not only does the alternator provide power to the electrical system, it also charges the battery. The battery is mainly used to start the engine or to power the equipment while the engine is not running. In cold weather, the battery capacity can be severely reduced, so it's important that the pilot conserves battery power. The electrical system is protected either by circuit breakers or fuses. Most modern airplanes are equipped with circuit breakers instead of fuses because they are resettable. A circuit breaker pops when there is excessive voltage, which results in high heat in the electrical wire. Fuses are not the popular choice today. Although they work similar to a circuit breaker, once a fuse burns, it must be replaced, and that electrical circuit will not be complete until that fuse is fixed. Circuit breakers are usually grouped together in the cockpit by the bus they are located on. Not the bus that brings you to school, but an electrical bus. An electrical bus is like a power strip. You can plug multiple things into a strip, and if you turn that strip off, everything plugged into that strip will not be powered. In an electrical system, the same remains true. The components of an electrical system are usually divided into multiple buses. For example, there may be a main bus and an avionics bus. On the main bus, main equipment such as lights are powered, and on the avionics bus, most of the instruments and equipment to run those instruments are powered. While there may be one electrical bus or many, the entire electrical system needs to be powered safely in order to prevent a possible electrical fire. In order to do this, a voltage regulator and alternator control unit work to monitor and control the electric system. The voltage regulator will allow the alternator's generated power to charge the battery and power the system with an acceptable voltage by stabilizing the output of the alternator. Finally, the pilot can monitor the electrical system by either an ammeter or a load meter. An ammeter shows the performance of the electrical system. If the alternator is providing sufficient power to the electrical system and is charging the battery, then the ammeter will show a charge. If the alternator is not charging the battery, or the battery is being used because the alternator has failed, a negative indication can be seen on the ammeter. A zero indication simply means that it is neither charging nor discharging the battery.
Zero.
While an ammeter shows electrical performance of the alternator in relation to the battery, A load meter shows the load that is being placed on the alternator. So if the alternator's load is 40 amps, then the indication will show 40. If the load meter shows 0, then the alternator is either off or has failed. If the alternator fails in any electrical system, the battery will provide power, but not for very long. Depending on the airplane and if there are any backup batteries, an alternator failure may require a diversion from the planned flight.
I seem pretty simple. I like the illustration where they use the power strips because we've all done that before. And a lot of airplanes run like that. Our 120 doesn't have circuit breakers, has fuses, so if a system goes bad, you have to unscrew the cap, take the fuse out, look at it, and replace it. The reason for fuses over a circuit breaker is because if there's a problem with that circuit that caused that fuse to blow, we don't want to go just replacing it. We want to land the airplane and figure out what's wrong with it, because that could be a fire potential. Any questions on electrical systems? I mean, they could be way more complicated, but you just need to know how to turn them on. All right, we talked about Wayne Hanley's crash the other day.
Yeah. Oh, man.
Can't believe you
He's
walked
a
away.
local pilot. He's
A lot of horsepower to be able to just take off and go straight up on it.
He's got like a vertical record or something.
So this guy flying, he lives at Pine Mountain Lake. He was one of the best air show pilots.
Just
of,
amazing.
of
Did
a
you get to see
generation.
him?
I was there.
Oh, that's right.
Yeah, I was 6 or 7.
Wow. That's crazy.
It just died.
Engine
right
quit.
after that.
Yeah,
Oh,
so
really?
he's
Right there,
done
quit.
pull up.
So he's counting on all his
He's
horsepower.
trying to get the.
And there goes that beautiful.
And he lived.
So glad
I wouldn't show you video if a guy was killed in it, 'cause I don't like that stuff. That's pretty amazing.
Wow.
And he's an inch shorter after that. That's why he hobbles a little bit. But I mean,
What did you?
to see Wayne today, you wouldn't know that happened. You know, which is
Do
really.
you remember when you were there? Were you just like?
I
oh,
remember my
that's
dad
it?
squeezing me.
Yeah.
You know, we were down, and I was kind of what happened.
That is wild.
But I've seen the video so many times that my mind's kind of filled in the blanks. But yeah,
What a beautiful plane.
oh, it's a cool
That thing's
airplane.
So amazing.
It's a cool airplane. We gotta do a lot.
Yeah, you need that power to arrest that.
Airplanes and
Have to look at
halls or something.
YouTube
All right,
and see these shows.
ice.
It's the craziest
And anyone tell me why ice on the wing of that airplane might be a bad thing?
Laminar flow.
Wait.
Laminar
Those are two perfect answers right there. Right? A, weight, it's super heavy, and B, it changes the shape of your wing, right? I mean, look at that. The air's not going to flow over that wing. That wing is no longer as efficient as designed, so therefore it makes less lift. And you're heavier because you're carrying all that weight of ice. That airplane could stall at any minute, and you don't know where it is. So some airplanes, mostly bigger airplanes, have ice protection and anti-ice systems. Anti-ice is like this black area here is called a boot. And what it is it's a giant airbag that gets pumped full of air, and it gets bigger and it pops the ice off of it. The ice generally forms on the leading edge of these parts, but you can see it's going a ways back here. So just popping off the leading edge isn't quite enough. You can see where the ice has kind of been broken. You can see little layers of there. There's not a ton of buildup, whereas the buildup is down here. So these boots were working when he landed. Okay, let's talk about airplane maintenance requirements. So you as the pilot and commander of an airplane are responsible for making sure the airplane is airworthy and safe for flight. What does that mean? You're not a mechanic? You're not a mechanic, so you got to know this stuff. Aircraft inspections. Each airplane is required to have a yearly inspection. You often hear called an annual inspection. It must be done every 12 calendar months. or 100 flight hours. You'll also hear the term 100-hour inspection. They are essentially the same inspection. If an airplane is flying a lot because it's in flight school, it needs to have the same inspection done. Airplanes also have an ELT, and we'll talk a little bit more about the ELT later. That's called an emergency locator transmitter, and that's designed to transmit a beacon on a special frequency when the airplane crashes. It's got a little accelerometer in there. When you hit the mountain, it's going to start transmitting on a frequency to help search and rescue crews find you. We have to test that every year, and if for whatever reason it inadvertently goes off because you had a hard landing or something, and it's running down the battery, we have to replace the battery if it gets less than 50%. Ultimately, that means somebody says, hey, the ELT was going off. We don't know how long it's going off. We don't know it's 50%, so we have to change the battery. And then you also have the transponder and pedostatic system. This is our transponder. It's a radio you'll see in some airplanes. The 120 doesn't have one, but the Pacer does. There is a 24-month check on those. 91-413 is the test of the transponder to make sure it transmits altitude correctly, and you need that if you're going to fly into certain airspace that requires a transponder. And 91-411 is for the pedostatic system. That is all of the pneumatic tubes inside the airplane that control the various instruments that are needed for flying in the clouds. So since our airplanes aren't certified to fly in the clouds, we don't do one of those inspections. 120 doesn't get this inspection because I have a transponder, but you're required to know what the status of that inspection is when you're pilot command. Now, with our airplanes here, this is a bad example. It drives me nuts that somebody would rent you an airplane and tell you it's fine and expect you as the private pilot to know if it was legal or not. You're not looking at the airplane's logbooks every day. So if you rent an airplane from us, you pick up this binder here, and right here is airplane status sheet. What airplane it is gives you all this information here. Annual completed date, the hours at the annual, the next due date right there, 5/23, 100 hours due at 343 hours. Oil change is due at 555 hours. ELT batteries are due. It gives you all this information so you don't have to guess. Don't overfly 255.95 tack time or October 8th. So you should be able to look at that and go, yeah, here's the time on the airplane, look at it, go, it's good. Actually, you should be able to look at this, the last person that flew it, they wrote down the time, and you should go, yeah, that airplane should be legal for its flight based on that. So we do that to try to make it easier for you as the renter. ELT, emergency locator transmitter. They're carried on almost all U.S. registered airplanes, and they transmit on 121.5. You'll hear that called guard frequency sometimes, and 243.0 is military frequency. Newer ELTs transmit on a 406 megahertz thing, and that's pretty common now. Most ELTs have been replaced with a 406 megahertz ELT. So numbers you need to know, 121.5 and 406 are numbers. You'll see what frequency does an ELT transmit on. It'll be one of those, your question will be one of those two answers. There's no sound of this one. This one's good though. So that's a gal. She's got some clackers on her to do this. Like, oh, just strap this wheel onto your shoulder and hang on to the airplane and go fix this wheel on this Jenny. This is a Curtiss Jenny. It's a World War I vintage airplane. So this is probably about early 20s or so.
I've seen this.
So this was a stunt back in the day, and I don't have the specific details, but this was a stunt that they were doing deliberately. But she was subsequently fined by the early FAA because she didn't have a mechanic's license. So it just goes to show you, if you're going to make a YouTube video, you better be legal, right?
That's what they got 'em for.
It's YouTube busting YouTuber, FAA busting YouTubers is nothing new.
That's good.
I like this girl.
Yeah, I like her too. This is probably Downey, California, right? This is probably, South Central Los Angeles right now.
Oh, gosh.
Everyone's been
Especially
jumping
putting
out
up
of their
pilots,
airplanes
too.
recently.
Oh, yeah, the Red Bull.
And Trevor Jacob.
Oh,
We
yeah.
don't need to talk about that Yahoo.
Dang. That pilot's kind of relying on her as well for his
Yeah.
landing.
So real.
I think normally the pilot be sitting in the back of that one. And my guess is he's sitting up front so he can keep an eye on her better. Not that anything he's doing is wrong. Just don't hit the other airplane, right? Couldn't pay me enough money to do that.
She never got it.
What a beautiful landing. I love that. That was a good one. All right. Airworthiness. You'll hear this term a lot, and it's important. Airworthiness is the condition of the airplane. It's two parts. It's physical, what kind of condition and shape the airplane is, the airplane, the propeller, all the parts. Do they conform to the original type design? And has it been inspected in accordance with Part 43? Here's the book I told you guys to get, the FAR AIM. Part 43 is actually not in here. It's kind of a bummer. Part 43 is maintenance stuff. That's the stuff I have to worry about as a mechanic. Is it all good? And the answer is yes. But you can't rely on the mechanic to tell you that. You as the pilot are ultimately responsible. So there's a lot of stuff to learn on this, and we're just going to graze the top. But the second part is the legality. In Part 91, which is our rules of the road that you'll see in your book, and it's the one section that's worth reading. It does have an annual inspection or 100-hour inspection. Airworthiness directives are something put out by the FAA saying, hey, we've discovered in the course of numerous flight hours of this type of airplane that there's an unsafe condition. This part cracks, or this part breaks, or it doesn't work. And so they issue what's called an airworthiness directive, or AD, and that's a required maintenance thing on an airplane. And mechanics have to take care of that stuff, and there needs to be a record of it. And that's usually kept in the log books of the airplane. So here would be a set of log books for our 120. Most of the time, flight schools will just hand you some books like this. I'm considered the paperwork Nazi in airplane maintenance. But over the years, a maintenance repair sign-off might look something like that. But this doesn't talk about the airworthiness directives. So this airplane's not actually legal because none of the airworthiness directives were said to have been complied with. Now they were, but if it's not written, it's not technically right, and then you, the pilot, could get in trouble. Other things would be the weight and balance form. Every airplane needs to be weighed, and a list of any revisions or changes to the equipment on the airplane need to be recorded. And you as the pilot use that to know that, hey, this airplane weighs this much. So when you're trying to figure out if you and your friend and your bags are going to fit in that airplane with your planned fuel, that you're within the airplane's legal center of gravity limit. And we're going to talk about weight and balance next. That's going to be tough to get through, I think. Here we have, this is called the airworthiness certificate. And that needs to be in every airplane. If it's not in the airplane, it is not legal. And the Cessna 120 has one of those, the Pacer has one of those. When you get on a 737 Southwest airplane, there's one of those. And believe it or not, it used to be if you walked in that 737 and you went, swipe that airplane could not leave without that little piece of paper. They've changed that now. This is the registration certificate. In the last 15 years, they made them expire, so there's now a expiration date, so you want to make sure that's current. And we also put copies of them inside one of these binders. Here would be a flight manual that would be in the airplane.
They don't get you every year.
They are good for 5 years.
Yeah.
It's not a thing you have to worry about as the pilot fixing, but you got to make sure it's current. And this should be displayed with the airworthiness as well. Somewhere when you open up that airplane, it should be easy to find where they are. They're supposed to be within plain view of the pilot. And who's responsible? 91.7. Pilot command is always responsible for. Pilot command is responsible for determining the airworthiness and if the airplane is safe for flight. That's why every time there's a crash or something, and a news story, they say, oh, it was pilot error, because 91.7 pilot's responsible. If the mechanic did something wrong, and you said everything looks fine and you took it, then you're at fault. The documents you have to have on the airplane. We use the acronym AERO. It stands for Airworthiness Certificate, Registration. Used to be a thing called an radio operator license. That's been not a thing for a long time, but was the second R in AERO. O is your operating limitations. That's generally an experimental thing, but there's also something called the limitations section of your flight manual. So this could be your airplane flight manual here, and you'll flip to a section called limitations, and that means this needs to be in the airplane. So this actually has to be in the airplane at all times. W is your weight and balance report. And other things you might find would be a flight manual. Here's a flight manual. This one they call an owner's manual. There's a bunch of different names for it. Pilot Operating Handbook, POH. You might see flight manual. They have a couple different names based on when they were certified. Flight manual supplements. This airplane has a couple of flight manual supplements for the installation of a bigger engine. This was certified with 135 horsepower and now has 150 horsepower. So that changed a number of the performance requirements of the airplane. The airplane used to say it would take off an X feet at X altitude. But we've got a bigger engine now, so it does it in shorter distances. So that's a flight manual supplement. So that also needs to be in the airplane. So our airplanes, we put them in these red binders, and this lives in the airplane. You wouldn't take this out. But right here are, there's a flight manual supplement. It's that goofy wingtip on there that droops down. In the 60s, they thought that'd make it take off shorter. So it has a flight manual supplement that's got to be there. So that's for that wingtip. Here's one for the bigger engine. And look, it gives you new CG range. So this was our original flight manual that has to be in the airplane. This is what originally came with the airplane. And it gave you some numbers, performance numbers, weight and balance stuff. But because there was a change, you have to now revert to the most recent revision here. So this is a little complicated to talk about it, but here's a copy of your airworthiness certificate. It's usually what they look like. I put a copy in here, but the original should be in the airplane. So this is called the supplements book. So I put all the documents you need to have in that airplane are in this book, and this shouldn't come out of the airplane. And we have duplicates available here for if you're gonna study the airplane. But here's the original flight manual for that airplane. So this needs to be in there along with that red book. And something that everybody misses is a fire extinguisher log. If there's a fire extinguisher in the airplane, it needs to have its maintenance done, the same as an airplane needs an inspection. And if you look at the sticker on the fire extinguisher, it says every 30 days has to be inspected. So you need to do that. So in the back here, we've got a fire extinguisher log, and it's easy to inspect. You look at it, you weigh it, the instructions are right on the sticker. And if it's got VOR navigation equipment, every 30 days it needs to be tested for proper calibration if you're going to use it for instrument flying. None of these airplanes are, and that's an instrument flying thing, so you don't need to worry about that. Weight and balance. I'm going to try to rip through this because there's a lot of slides. It's real tough stuff. Don't worry if you don't get it, because this is real tough stuff. Anybody got the time? Oh, we're not getting through this in 15 minutes. Are you kidding me? All right. Any airplane, any item on the airplane that increases total weight is undesirable, because it's gonna affect our performance, right? So airplane manufacturers attempt to make the airplane as light as possible without sacrificing strength or safety. The pilot of the airplane should always be aware of the consequences of overloading the airplane, because the airplane may not be able to leave the ground, or if it does become airborne, may exhibit unexpected and unusually poor flight characteristics. If an airplane is not properly loaded, the initial indication of poor performance usually takes place during takeoff. If you put too many people in the airplane and too much gas, the airplane, if it gets up, is all of a sudden not going to clear that tree at the end of the runway. Excessive weight reduces the flight performance of an airplane in almost every respect. Higher takeoff speed, longer takeoff run, reduced rate of and angle of climb, lower maximum altitude, shorter range, reduced speed, reduced maneuverability, higher stalling speed, higher approach and landing speeds, longer landings, excessive weight on the landing gear. Weight of the airplane can be changed by altering the fuel. Gasoline is considered weight. It weighs 6 pounds per gallon. So 30 gallons of gas could weigh more than a single passenger. You gotta remember that if weight is lowered by reducing fuel, the range of the airplane is decreased. Starting to pick and choose how much gas we're gonna take on our trip, it can kind of start getting dangerous if you go, yeah, really want to be able to take my friend in my bag, so let's put less gas in it. Are you gonna have enough gas for the trip? Are you gonna have enough gas to pick an alternate airport? If you wanna go from here to Truckee, and Truckee's closed or too windy, do you have enough gas to turn around and go to Auburn or Reno? This is all stuff that you have to work on planning when you are planning your trip. Balance refers to the location of center of gravity of an airplane, and it's important to safety of flight. The CG, or center of gravity, is a point at which the airplane would balance if it were suspended at that point. Here's our airplane. That's probably about the CG, right? I could probably balance it right about there somewhere. But if you put people here and you put gas here, is it balanced anymore? It's not, right? Prime concern of balancing an airplane is the fore and aft location of the CG along the longitudinal axis of the airplane. The CG is not always a fixed point. Its location depends on the distribution of weight in the airplane. Variable load items are shifted or expended, meaning gas, as you burn it up or it moves. There's a shift in the CG. And so the pilot should realize that if the CG of the airplane is displaced too far forward, a nose-heavy condition will result, or if the CG is too far back, a tail-heavy condition will result. And it's possible that an unfavorable location of the CG could produce an unstable condition if the pilot could not control the airplane. Here's a nice picture for us. This wing here, our left wing is full of gas and our right wing is full of gas. Kind of makes sense which wing's heavier there, right? Same goes for the lateral loading. We put the baggage here, maybe the tail's a little heavier. As we move it back, the tail is going to be more heavy, right? Location of the CG with reference to the lateral axis is also important. Not as important though. For each item of weight existing to the left of the fuselage center line, there's an equal weight existing at the corresponding location on the right. This is talking about the fuel in the gas tanks. If I am by myself in the airplane and sitting in the left seat, and I'm burning fuel from the right tank, we're starting to get heavier on the left side, and that can affect how the airplane flies. I got a lot of these because this is important, and we'll probably go a little long here tonight. The forward CG limit is often established at a location that's determined by the landing characteristics of the airplane. Tailwheel airplane here, if you put too much weight in the front, it's going to tip over, right? It probably would have to be a lot of weight for the airplane just to sit here and tip over, but when you're landing and your momentum's going forward, that airplane already has a tendency to want to tip over. Think of talk a little bit about tailwheel airplanes. Think of the tailwheel airplane as riding a tricycle backwards. Your weight is behind the main wheels, so your weight wants to come forward of the wheels. A shopping cart has the caster on your wheel here. The axle is behind the center of gravity, right? The CG of this thing's probably up here somewhere. And so that's why the axle here is trailing behind the CG. Tailwheel airplane wants to do the same thing.
Driving a forklift at 40
Right?
miles an hour.
If I start pushing this thing this way towards me, what's that wheel gonna do, right? It doesn't wanna go that way. The CG's behind it, it's gonna come behind the CG. So loading the tailwheel airplane is, and then an airplane, but I could make landing that airplane more difficult. Like when we talked about the weight of the ice on the wings of the airplane, overloading the airplane is, I mean, it's pretty simple. Put too much weight in the airplane, it's not gonna fly. It's designed to carry X amount of weight. That's really all it carries. Now you'd be surprised at how much weight maybe something like that actually can carry, but it becomes safe and it's actually not legal to overload the airplane. Up-to-date information. You know, oftentimes what happens on an airplane is, especially you as a renter, is they take a radio out and replace it with a different radio, and they're removing and replacing equipment. They're actually changing the weight of the airplane. And we can guess as to, hey, this radio weighed 5 pounds, we put in one that weighed 4 pounds. The airplane weighs a pound less. But there's also a thing called your weight and balance envelope. Based on the CG of the airplane, you could put X amount of weight forward of the CG and X amount of weight after the CG. And that's why an up-to-date weight and balance form is important for you to make the right calculations. So here's some terms for weight and balance here. Arm, or known as moment, is the distance from a reference point. So a lot of airplanes would use the firewall or the very leading edge of the wing, and that's referred to as the datum. And then any number of inches beyond that would be called a station or an arm station. And we just use inches because it's easy. So if you were to put something in the back seat of that airplane there, how many inches is the back seat area from the leading edge of the wing? 50 inches, something like that or something. So the back seat arm would be 50 inches. Basic empty weight means what the airplane weighs plus any special or optional equipment. Don't worry about special optional equipment. What that airplane weighs empty with no gas but full oil is that airplane's empty basic weight. You're going to figure out how much you and your passenger weigh, how much your bags weigh, how much gas you need weighs. You're going to see if it's within total weight and within the CG range. We're going to do a test problem here. Center of gravity limit. You can only go so far forward or aft. Range is the distance between the forward and aft. Datum is the reference point. Fuel load is the weight of the fuel, right? That's pretty easy. Licensed empty weight. Some airplanes have a thing called licensed empty weight. You probably won't see that very much. Maximum landing weight, that gets into airliners. You know, if they take off with a bunch of gas to go to LA to New York or something, they take off out of LA, go, we got a problem, we gotta come back. They've got all this gas that they either have to burn, dump, get rid of before they can land, or when they land, they actually have to inspect the airplane and make repairs. Maximum ramp weight is similar. Some airplanes can weigh more on the ground than their maximum takeoff weight. Get an airliner thing because they're expecting you're gonna put a ton of gas because you're gonna use a lot of gas taxing the takeoff. And so we put a little bit more gas on ahead of time. So when you're ready to take off, you've got your maximum fuel that you can use for your trip. Maximum weight is what it sounds like. Zero fuel weight, again, an airliner thing. Mean aerodynamic chord, ignore that word altogether. Moment, that's the product of the weight multiplied by its arm. You take a 10-pound bag, you put it in the back seat, we said that was 50 inches. The weight of 50 pounds times 50 inches. Anybody want to guess that number? 50 times 50? It's 5 times 5. 2,500. Payload, standard empty weight, makes sense. Standard weights. So when we're planning our load in the airplane, it's pretty simple. We go, gas weighs 6 pounds a gallon. If it's a jet, 6.8. Jet B, you're not going to see that, you know. Oil, 7.5 pounds a gallon. It's just standard weights we use there. And water, how much water weighs. Station, kind of similar with arm, would be a predetermined location. You know, if we said back seat with 50 inches, that would be back seat station. You got front seat station, you have fuel station. Any piece of equipment could have a station, but that relates to an arm. Useful load is how much weight the airplane can carry. Passengers, pilots, bags, fuel, anything else you might put in.
Do they usually add a factor of safety on that for people?
Well, in these little airplanes, there's a maximum weight, which you can legally go up to. The useful load on our Cessna 120, the way it weighs, I think we can carry 504 pounds. So I'm 260. How much do you weigh?
A lot.
You know,
We've
if I'm 250 and it was 500 pounds,
There's no way.
we're not flying that airplane. Right? I mean, it's pretty simple. There's a little bit of drawing. So this one, they're using the engine firewall as the datum. So any arm forward of the datum is a negative number, and anything positive aft is a positive number. You're putting your bags and your people and stuff here, so that helps. That's a positive number. You're not doing so much up front, so adding a negative number to the equation is not so difficult. Some airplanes will put the datum out here, so all your numbers are positive. So here's our CG range, those little triangles. Our weight, you know, if I put this airplane on my finger, it's going to bounce on my finger in that range, or that has to be. It has to be in that range. It could be outside. If I put too many bags back here, I might want to tilt down outside of that, and it won't be legal. I think I've got a better one next. Let's see. Okay. Memorize this. Weight times arm equals moment. This is the equation that you're going to get on your test. And this is going to be on your practical exam with your examiner. And he's going to make you do a sample weight and balance problem. When you show up to your check ride, he's going to tell you ahead of time, I weigh 250 pounds and I've got a 10-pound bag that's going in the back seat. And so you're going to figure that out, and you're going to bring that with him and go, here's where we are, and we're good to fly with the airplane that you bring over. All right. Assume a weight of 50 pounds is placed at a point 100 inches aft of the datum. Weight 50, arm 100 inches. 50 times 100 is going to give you your moment, 5,000 pounds. I think that was our figure we saw. Here it is. There's our weight times arm equals moment. Here is our 100 inches and our 50 pounds. So weight 50, arm 100, our moment is 5,000 pounds. It's a pretty easy formula. So, here, imagine this is our airplane, and here's our CG. You've got some weight in the back, and we've got maybe 2 pilots up here at the front. Is it going to be balanced? Well, weight times arm is moment. 100 inches times 50 is 5,000. Weight 100 times arm 25 is what? Okay, 2,500. 100 times 25, 2,500. Then we also have weight of 50 at 50 inches. 50 times 50, 5 times 5, 25, 2,500. So our total moment is 5,000. Our total moment here is 5,000. That's going to balance. I mean, I probably couldn't have figured it out in high school, but it makes sense to me now. All right. Okay, we're going to do a sample problem. All right, for those of you who brought notepads, let's try this. The airplane weighs 1,450 pounds. Or, sorry, the max gross weight of the airplane. The maximum that airplane can fly with, 1,450 pounds. But currently, the airplane empty weighs 944 pounds. Our CG range is going to be 13.5 to 17.7. Pilot 1 weighs 250 pounds at 38 inches. Weight times arm, it's moment. Pilot number 2, say 350 at arm 38 inches. That's the 38 inches there would be the front seats of the airplane. Is going to give you a value. Say we have 10 gallons of fuel at 42 inches. How much do we say gas weighed? 6 pounds a gallon? And in the baggage, we're going to put 5 pounds at 44 inches. Weight times arm gives you a moment. List the weights of the airplane, the occupants, fuel, and baggage. Enter the moment for each item listed. Total the weights and total the moments. Once you have that number, divide the total moment by the total weight. Anybody got an answer for me? Total weights. All the moments there. Weight times arm moment. There's our moments. Boom. There's our total moment. 17,940. We're going to divide that by our total weight. $12.73. What was our range?
13.5.
13.5 to 17.7. Are we in the CG range? No, we're not. So we can't fly. So the 250-pound pilot, the oh, this got mixed up there. I think the last page was supposed to say 150, not 350. Either way, we're not in the range. Okay, but I guess the last slide did say 350. But is our total weight here, are we beyond the max weight of the airplane?
No.
944 plus 250 plus 150 plus 60 plus 5 puts us at 1409, and our maximum gross weight was 1450. So we're under the max gross weight, but our CG is too far forward.
Shift it around a little bit maybe.
Could do that, right? Well, but let's
Oh,
say
it's
this
back
is the 120,
Yeah. No.
and you can't put any pilots in the back. You can't move the fuel around. The fuel is where it's at.
All
You
have
could
to do
maybe
is-
put
Strap a wrench.
you could maybe put more weight in the baggage compartment to try to move that back. Under maximum weight, yes.
Could you adjust the fuel?
You could take less fuel, just because I know that this airplane, lesser fuel isn't gonna change your CG range. So, all right, let's try another one. Same airplane, max gross weight is 1450, airplane empty weight 944, same CG range. Let's say it's a 250-pound pilot at 20 inches. And second pilot, let's do 350. Make this 150 because 350 we're going to be way outside of weight. So 150 weight times arm, 150 times 20. Fuel, put it in a chart, makes it easier. Oh, and then this thing got messed up. Now this is 175. I don't know what the heck happened here. I mean, I did all this. All right, so pilot 2 is 175. We add up our total weight. We add up our total moment. We get our total moment 13,660. Divide the 2, right? 9.5, is that within our CG range?
No.
13.5, right? Nope. So that didn't change any for us, right? We're under max gross weight, but we're not within CG range. Can't fly. All right.
So then we should, yeah, that makes sense that we shift it around. Sometimes we shift it.
How does an airplane's weight and balance affect its performance? Let's build your own airplane to find out. Here's a fuselage. Its weight will pull it downward through its center of gravity. And what's an airplane without wings? As you know, the wings lift and induce drag forces act through its center of pressure. Usually this is slightly behind the center of gravity for stability, just like an arrow has its heavy nose ahead of its draggy tail feathers. In order to fly level, our forces need to be balanced and aligned. If the wings aren't over the center of gravity, then our fuselage will pitch out of control. So what's the solution? Add an elevator at the back to adjust and control pitch. To keep the nose level, which way should the elevator push? Down. Exactly. Now that the total downward forces from the weight and elevator is equal to the upward lift force, we can maintain level flight. Let's start loading the payload at the front. Which way will the CUG move? And how do we compensate? The elevator needs to push down harder. Since our total downward forces have increased, the wings counteract by generating more lift upward. And what also increases with more lift? More induced drag. So if you have a forward center of gravity, you'd cruise slower with the same power setting. Can you explain why a rearward CFG would lead to a faster cruise speed? The elevator doesn't need to push as hard, so the total downward force is less, and the wings don't need to generate as much lift to fly level. Less lift means less drag, and you can fly faster with the same amount of thrust.
Clear as mud. The best analogy there was the arrow. I mean, if you can picture an archery arrow, you've got those feathers at the back to make it drag you back there, and you've got the arrow point, which has some weight to it, actually keeps it stable in flight. That's why they're long. If they made them shorter, they'd be less stable. Think about a model rocket or something, or paper airplane. You know, those long pointy paper airplanes fly the best, right? Because they put a lot of weight up here. All right. It's boring stuff, and we really skimmed through it. I would recommend maybe reading through the slides and studying up on it a little bit. You could probably go to YouTube and watch a handful of videos, which probably make it a little more entertaining. But it's important stuff because you're gonna have to, you really have to do a weight and balance calculation for every time you fly the airplane. Not so much for every time you're gonna get in the 120 and go fly by yourself, because you can go, hey, I know by myself I can have this much gas or this much maximum gas or this minimum gas, you'll be okay. One thing that does affect performance is things like density, altitude, and the temperature of the day, and we'll talk about that later. But as you get into a different airplane, you don't really know how to load the airplane, so you're gonna be doing a weight and balance calculation a lot when you're flying. Once you get beyond your private pilot license, you start flying other airplanes, or if you get a job pulling, if you're pulling banners, you're not going to be doing it much. But let's say you got a corporate job and you're flying people around in a Pilatus or something. You need to know how much those people weigh and where they're sitting, and if the airplane's going to be good. Something like a PC-12 job would be taking people from here down to Palm Springs to golf. They might be putting a lot of heavy golf bags in the back. So one job I have out of Modesto is how many people are coming on the flight. We got 6 people. Okay, you each have a 25-pound bag. That's your maximum. Or if it's 3 people, you can have a 100-pound bag. But otherwise, the airplane's overloaded and we can't carry that kind of weight. All right. We haven't even touched on turns yet. Does anybody want to keep going or leave or do this next week or anything? We could try to breeze through it. Probably, I don't know how long it'll take. Feel free to speak up. If you're saying, I gotta go, whatever, then.
I'll get on work up there.
Yeah, we had a good 15-minute delay there.
Hey guys, what's going on? John here from FlyMikeAlpha.com, and today we're going to be going over turns about a point. Everything you need to know about them, how they're done in the airplane, all the tips and tricks to know, and what it ultimately looks like. So first, let's go ahead and define what a turn about a point is. Ultimately, it's simply a maneuver where you're flying relatively low to the ground and you're making a circle around a defined point. The purpose of this maneuver is to practice changing your bank angle or changing your rate of turn to accommodate the wind. So to account for the wind that's trying to blow you away from the point. If we were to simply circle a point and not change our bank angle ever, well, the airplane would be drifting with the wind that is blowing up at altitude, and you'd eventually get blown away from that point. We're trying to control the airplane in reference to what's on the ground, because ultimately, you're going to be making turns in the traffic pattern and trying to get lined up with the runway, which is on the ground, and the wind up high is going to be blowing you away from or towards the runway or affecting you in some way that you're going to have to account for. So what are we looking for completion standards on this maneuver? Well, the skills as defined by the ACS to complete a turn about a point, a ground reference maneuver, are going to be first, to clear the area. The student selects a suitable ground reference area, so you're selecting a good definable point. I really like choosing two intersecting roads, where you have 90-degree roads, to really choose that, compared to trying to choose something large and arbitrary like a lake or a runway or an airport or a house. Choosing a very small defined point. We'll talk about that more later, choosing your appropriate point. Next, you need to plan the maneuver appropriately. This maneuver should be planned to be done between 600 and 1,000 feet AGL. So I like to aim for 800 feet AGL because you do need to stay within that 600 to 1,000 foot AGL envelope, and they are also looking for you to maintain your altitude plus or minus 100 feet. So by choosing 800 feet, that gives you plus or minus 100 on either side, keeps you within that 600 to 1,000 foot envelope very nicely. They also want you to try to maintain your airspeed within plus or minus 10 knots, and want you to divide your attention between airplane control, traffic avoidance, still looking outside the airplane, looking for other traffic rather than just staring at the point on the ground, and also monitor the ground track while maintaining coordinated flight. So look at the points on the ground, make corrections with bank as necessary, using your ailerons and rudder together to stay coordinated. Don't forget to use the rudder when you're using the ailerons during this maneuver. Now let's go ahead and look at how it's actually done. So your first step is going to be determine where the wind is coming from, and not necessarily where the wind is coming from the ground, but where the wind is coming from aloft. So if there's a big difference between the wind at 1,000 feet and the wind at the surface, you'll want to use the more accurate, the wind at 1,000 feet. Oftentimes, you can simply use whatever the wind is on the ground. So if it's coming from 270 at 10 knots on the ground, it's probably relatively the same, 600 to 1,000 feet above the ground. Next, you're going to want to start on the downwind. So you're going to want to start with the wind on your tail. So after you've selected your point, like we said earlier, I like to choose 2 intersecting roads and aim for the exact middle of the intersection. Aim small, miss small. So don't choose a large target like a lake or like a clump of trees. Choose something very tiny and defined, like a windsock at an airport, or like 2 intersecting roads. Something very tiny and defined. Also, make sure when you're choosing this area, it's in an unpopulated area because you're going to be flying pretty low and you don't want to disturb your neighbors or break any other regulations of flying too low over people or property. So choosing an unpopulated area like this where there's houses a little bit further away and there's really nothing around there, plus there's some awesome fields to land in should you ever have a problem at low altitude like an engine failure. So now that we've determined where the wind's coming from, we're going to start this maneuver with the wind on our tail. On the downwind, very similar to starting your traffic pattern on the downwind when you first enter the traffic pattern at a 45-degree angle like we talked about in a previous lesson. So we're starting on the downwind, and as we come a beam or point, so as it's off of our left or right side, you're going to do this maneuver both to the left and to the right. As the point is abeam you, you're then going to roll into the maneuver, and because you're moving quickly with a high ground speed, because you have a tailwind at this point, it's going to require more bank angle initially. So the steepest turn will be when you have a tailwind. As you come around, you want to get your nose pointed slightly upwind to account for the wind drift. So as you come down to your bottom 90-degree point, that's when you want to have turned not just 90 degrees, but actually made about a 100 to 110 degree turn. So your nose is pointed slightly upwind and you're accounting for that wind drift. As you come around into the second 90-degree section of the circle, you're going to shallow your bank slightly, rolling not wings level, but nearly wings level as you come back abeam your point, working your way upwind. If you keep that bank angle in there, the trouble is you're going to keep turning and you're going to get blown too close to your point. You want to shallow the bank and get further away from it. Work your way upwind. As you start to get adequately far upwind into the third quarter of this turn, then you'll start to roll in the bank again, and you'll start to roll in steeper and steeper and steeper until you come into the fourth quarter of the turn, the last 90-degree portion of it, and you're going to be rolling very steep again because your ground speed is increasing and your rate of turn needs to increase as well to accomplish the turn in a quicker amount of time since you have less time passing that point. What you ultimately need to remember here is high ground speed, high bank angle, low ground speed, low bank angle. When you're going into the wind, shallow your wings, shallow your bank, and fight your way upwind so you can cover more distance before the turn happens. Now, when you have a high ground speed, make sure you steepen the bank and finish the turn before you get blown further away from the point. Ultimately, if you're getting far away from your point, steepen your bank angle. If you're getting too close to your point, shallow your bank angle. Those are the simplest ways to explain this maneuver, and that's ultimately all you need to remember in the airplane. The ultimate goal here is to make a perfectly round circle as if there was a pencil attached to the bottom of the airplane and you're drawing a perfectly round circle around that point, maybe a half-mile wide circle, 3/8 of a mile wide, 3/4 of a mile wide, whatever distance you choose to do this at. But ultimately, just don't get blown back across your points. The only way you could really fail this maneuver on a check ride is to bust the altitude, really bust your airspeed there, plus or minus 10 knots, or to get blown back across your point. Roughly inscribe a round circle onto the ground. That's all we're really looking for here. If you have any questions about this,
hey guys, what's going on? John here from FlyMikeAlpha.com, and today we're going to be going over turns about a point. Everything you need to know about them.
Gosh. He's pushing the wrong button or something.
That makes sense though.
So any questions on that?
No, that was good.
Does everybody understand basically what we're talking about there? Is if you're going to be flying around your point, and say the wind is coming this way, if I'm wings level here, I'm getting pushed this way. So I need to bank and turn into the wind in order to compensate for the wind drift. And as you turn, you're varying your bank angle to maintain that distance from your point and to compensate for that wind. And I'm going upwind, you could be almost wings level. Then as you start banking again for the turn, now that wind's wanting to push me this way, so I need to shallow out my bank so that I don't get pushed too close to the spot. And then you come wings low again, now that it's at my tail. Now you're going a lot faster, so you're gonna have to roll into your turn sooner. And all it takes is practice, but it's one of the maneuvers you're gonna have to do. Now one thing you talked about was completion standards. That's what the FA calls what you have to do on the check ride and pass. So your examiner is gonna evaluate you on that maneuver. And what he was saying about that one was just don't go low. Yeah, you really can't do that one wrong. Now, don't be stressing about, am I good enough to do this maneuver or not? If you're worried about that, then you're not. It's easy. Turning is easy. We'll go do it 5 times and you'll get the hang of it. You just get so overwhelmed with all the things that are going on that you're worried about doing these things on the check ride, but you're gonna find flying the airplane becomes very second nature. And the flying airplane part of the check ride is the easiest part of the check ride. It's all the knowledge stuff and the pressure of the test that really gets to most people. Test standards, I hear that a lot. All right, let's see. When an airplane is placed in a bank, the resultant lift is split between the vertical and the horizontal component. X lift is made when the airplane's level like this, but when you go like that, your vertical lift is less, right? Because there's less wingspan. But it's also making lift horizontally, that way, right? Equal and opposite reaction is centrifugal force. You all been on a roller coaster or flung a string around your head. The resulting force of that is inertia, and that's kind of what helps continue pulling an airplane through the turn once you've established a bank angle. Relationship between the airplane speed and bank angle determine the rate of the turn. There's something later on called a standard rate turn that you'll learn. Anytime the ailerons are used, adverse yaw is produced. So, we remember that the ailerons are on the trailing edge of the wing. Actually, we use this one right here. Which way is this airplane turning?
Right.
Left. Everybody out?
Left. Left. Rolling left.
You're right. Okay. So this airplane is turning to the left. What you have is this airplane, as it's rolling into its bank and turning, changing its heading, the other ailerons are producing drag. This aileron is now creating a bunch of drag. And so that pulls this wing back. That wing continues going forward. So as you start turning, this wing does that, and now the nose pitches kind of up, and that's called an uncoordinated turn. You use rudder to fix for that. A turn is used to change the heading or direction. Well, kind of duh. Ailerons bank the wings and help determine the rate of turn. Elevator moves the nose of the airplane up or down to set the pitch. The throttle provides the thrust, which is used for controlling airspeed. but the rudder doesn't turn the airplane. 3 types of turns: shallow turns, medium, and 45. You never really hear a medium turn, but there are marks on the attitude indicator to indicate those numbers. Two different objectives when doing a turn, practice turn. One is rate of turn, and the other is radius. Rate is the time it takes to make a turn, whether it's a 360 or a 180 turn, and radius of the turn is the size of the turn. Changing direction of lift causes a turn. We talked about banking there. Now we've got this horizontal lift that's going to help turn the airplane. Lift is a result of horizontal and vertical components of the airplane. As the horizontal lift increases, the vertical lift decreases, requiring rudder to keep the aircraft level. So now as the lift is pulling the airplane this way and there's less lift keeping the airplane up, the nose is going to fall, and so you're going to need rudder to compensate. Rudder controls coordination. That is, imagine through the vertical axis of the airplane, goes about between the 2 pilot's front seats. And if you were sitting in the back seat, you get it thrown around a lot. Using the rudder to coordinate the turn keeps effectively those people in the back seat not banging against the walls. The airplane is flying a coordinated turn, coordinated between the rudder inputs and the aileron inputs. If you put too much rudder, the airplane was going this way, that'd be called a skid. You don't want to be skidding the airplane. So as you're turning, lift is pulling that way, lift is decreasing this way, adverse yaw on the ailerons is twisting the airplane weird. You need to add that rudder to keep the airplane making a nice, pretty turn. I don't know if I'm explaining this with the RNO. All maneuvers done in accordance with the POH or standard operating procedures. That would be in your flight manual. There's that. I was looking for that. There we go. Right? Vertical component of lift, horizontal component of lift. There's your resultant lift because you've got less vertical lift, you've got more horizontal lift, and of course, weight of the airplane is pulling it down. Standard rate turn. You can enter a standard rate turn. This is a maneuver you're going to have to do on your check ride. You're going to apply a coordinated aileron and rudder in the direction of your turn. You're going to use your attitude indicator to establish an approximate bank angle. You're going to look at the coordinator for the rate of turn. There's a spot in there, it's called the 2-minute turn. It's a standard rate turn. You're going to put that needle right on the mark. And once established, the turn coordinated gauge becomes the primary bank, and the attitude indicator seconds the turn coordinator. VSI is vertical speed indicator. That tells you how much you're going up and down. And you're going to use your vertical speed indicator. I need a panel here. For adjusting pitch. If you see the vertical speed increasing, you're going to have to adjust your nose up pitch, either by pulling the power back so the nose wants to fall, or reducing the angle of bank. Airspeed is primary for, that's not right. Recovery out of the turn, coordinated aileron and rudder. That gauge is, there's a little kind of smiley face shaped glass tube with a ball that sits at the bottom. And as you turn, that tells you where you need to apply your rudder. That's your coordinated turn. Keep that coordinated turn going. As you roll out, you start rolling out. Less aileron, less rudder. You want to come out of the bank angle before you're heading. Just a couple of degrees before you're heading because the airplane is still rolling out. If you try to roll out, you're gonna end up being a couple degrees off. So you kind of roll out just a little bit early, and it's one of those things you do a couple times and get comfortable doing it. Heading indicator becomes your primary. What? That doesn't make sense either. I don't know. Copied a lot of this stuff. Magnetic compass turns. The magnetic compass is a tough thing to do because there's a lot of error in a compass. There's a thing called lead and lag in a compass, and maybe we'll say this for another time because this takes a little bit of discussion. Here's a thing to remember: accelerate north, decelerate south, undershoot north, and overshoot south. If you're going from a north heading, you're turning to the south. You need to go beyond a south heading because of the lag in the compass. I don't know how to explain that. We'll explain that later. That's a tough one. I don't think I caught that in there.
You're saying when you're heading south, you have to account for the lag for the compass to catch up
Mm-hmm.
to
Yes.
the North Pole
Yeah.
magnetic field. Okay.
You know what? I need to brush up on it because honestly, I haven't done it in 15 years.
Yeah.
Because this thing you do once for your private pilot test and then you're done. Time turns. If you're going to use a clock to time a turn, if you're doing a standard rate turn, and a standard rate is the 2-minute turn, and it's on your turn coordinator instrument. If you roll into that standard rate turn, and you have your little gauge centered on the 2-minute turn, then right there, you can time your turn. At 10 seconds, you'll be 30 degrees, 15 seconds, 45. And they call it a 2-minute turn because 2 minutes, you do 360 degrees. Any turn greater than standard rate is considered a steep turn. Everything just happens for you a little bit faster in a steep turn. Climbing and descending in turns, you're going to combine the technique of climbing with turning. I can't imagine anybody's going to have too hard of a time once we start actually doing it. Level turns procedure. One thing that your examiner is going to want to see, and it's a good standard practice to get into, is when you're up flying around, you pick a certain spot in the sky where you're going to practice maneuvers. It's a thing called a clearing turn. That's where you're going to look out the window and you're looking in front of traffic. And you probably can't see anybody behind you, so you turn a little bit to look around, make sure there's nobody, no other traffic in that area. And a clearing turn is not a defined maneuver, it's a safety maneuver. So if your examiner or instructor says, all right, let's do a turn to the left, you go, okay, well, I'm gonna do a clearing turn first. Do your left turn, okay, we're clear. Now we can do our turn. You're gonna end up doing standard rate turns for your clearing turns because that's gonna show the examiner that you know that pretty well. Pick a reference point or heading, straight for the security camera there. If you pick a point that's too close, the wind drift, or you might approach it and it might be in a bad spot, but a point too far off, you're going to have no appreciable change due to the parallax of a mountain off in the distance or something. Picking a point. Oh, I guess it's talking about if you're trying to turn to a point over there, pick your point. Not moving. I don't know what that means either. All right. primary instrument for pitch in a turn is your altimeter. Your primary instrument for bank in a turn is your turn coordinator. Your primary instrument for power in a turn is your airspeed indicator. When you're in a turn and you're looking at your altimeter to make sure you're not pitch is climbing or descending and make sure you're not going up or down, you can also look at your attitude indicator, or VSI is vertical speed indicator. When you're in a turn and you're banking, you're looking at your turn coordinator. I sure wish I had a picture of these. It's got a little needle, put it right on the mark. You've got your standard rate turn going, but you can double check it by looking at your attitude indicator. Your attitude indicator is the blue and brown one. And when you're in the turn, you're mainly looking at your airspeed for your power setting, but you can also be looking at your tachometer RPM gauge. Common errors when doing turns: failure to adequately clear the air. That's the safety turn or clearing turn. Attempting to execute the turn solely by instrument reference. You still need to kind of look outside in the airplane. And an important rule is you always need to be looking outside, because you always have to be looking for other traffic. People try to sit straight up in relation to the ground. The airplane's in a turn, and the pilot tries to sit up. That doesn't help your quality of a turn. Or you don't have a good feel for the airplane, and you can't detect slips or skids without referencing the instruments. What that's talking about is, we were talking about the airplane skidding through the turn. If you were in the back seat, you'd butt be sliding all over the place. You feel that in the front seat too. It's a little harder for somebody that hasn't spent a lot of time in an airplane to notice. And the only other way you can notice them is by looking at your instruments. You'll develop that feel in your butt. You won't need to look at those instruments to complete your turn, because you can feel it in your butt. Your instructor is certainly going to feel it. That's just one of those things that comes with experience. And attempting to maintain a constant bank angle by referencing the airplane's nose. You get to change your bank angle in a turn. A lot of people think they set it and they got to keep holding it. And that's not true. You get to change your bank angle. Don't fixate on the airplane's nose. You're looking ahead of the turn. You're looking at your instruments to support that you're doing a correct turn. Flat turns would be skidding. So imagine the airplane trying to turn to the left, but you're putting the nose up because you're afraid of the ground, because in a turn, you're maybe closer to the ground, or you're looking down, or the nose of the airplane feels like it's coming down. Depending on how you sit in the airplane. Some people that are taller, they're looking over the nose, feel like the nose is way high, whereas shorter people feel like they can't see what the nose feel like the nose is high. Like a tall person feels like the nose is low. And some people are afraid of the ground, so they try to kind of cheat away from the ground, and that can mess up your turn. Holding the rudder in the turn. You don't want to hold the rudder just for the turn. You want to match your turn and slip indicator. A lot of people only do turns to one direction, and then you do them to the left because you're in the left seat, and then all of a sudden the examiner says, let's go right, and you can't do them to the right. And failure to coordinate use of the throttle and engine power. You have to blend all of these things to make a good turn. But one thing that happens is loss of altitude during the turn, or even gain of altitude, and you're allowed plus or minus 100 feet on your turn. So if you start a turn at 5,000 feet, you want a 180 turn, you need to roll out that turn at 5,000 feet. You get up to 100 feet. or above 100 feet, it's a bust on that maneuver. You don't have to do it again. I know there's a lot of this stuff, but don't get overwhelmed by it. You know, a lot of this text also is kind of meant more for me to discuss it, not so much stuff for you guys to study. I'm not much of a presentation maker. I know I can make one screen that I see and you see another thing, but I didn't do it that way. So we haven't really talked about what trim is in the airplane. Trim is that little tab on the tail of the airplane that helps right here. This is the trim tab. And the idea is that tab is designed to fly this elevator, which alleviates the load on the pilot's pitch control. And if you don't trim the airplane right, sometimes you're fighting an airplane that's out of trim. The nose wants to come up or go down, and so you're fighting it the whole time. It can make your turn or any maneuver hard to do. So you always need to learn to trim the airplane right. And that's easy. In the 120, it's a little wheel here. You just move it until you like it. And the pacer, it's a crank handle up here. Yeah, you gotta get that turned. Yeah. Well, all right. We'll try. Flight simulator games. You know, if you've got a flight simulator program, WingX, Microsoft Flight Simulator, I don't know if they have particularly great training programs built into them, but you can gain a lot of experience looking at the different instruments during a turn. The one thing you can't replicate is what it feels like in an uncoordinated turn. But if you had access to one of those I'm sure is good to play with for that. Any questions? I know we went real long tonight, but we came up short last week. So. Anything? No stupid questions, just stupid people, right? No? All right.
Would you prefer to fly a nose heavy airplane or tail heavy airplane?
I like to trim it out.
If it was as far as weighted.
Preference? I don't know.
Is one more erratic than the other? You think in yours?
Yeah.
I know with models, tail heavy is like that. Not good. Because then you're center right.
You know, I think the one thing, the difference about models is they have so much power to weight ratio.
Yeah.
You can, that airplane, the power that thing can pull it. It doesn't make any lift. That video last week where it showed the airplane talking about thrust, right?
Yeah, that's
it shows straight up. That's all thrust based. There's no lift there.
Yeah.
Yeah.
And that's
what makes it
kind of what I don't like about models, like in the sense for we talk about like the air show, coming to the air show or something. Is it's not really scale or something because they just so much gobs of power for everything.
Right. Yeah.
They don't just fall apart from low
I had a $100 foam thing this big. It went 100 miles an hour. I mean, I was blown away by that. You know, the 120 doesn't do 100 miles an hour, so airplane I can fit in. You know. So, cool. Well, let's see anything else. Go on. Cool. Thanks for coming, everybody. Sorry I went long, but. Boring stuff. Oh, it gets way boring when we start talking about weather. I'm gonna have my dad teach you guys about weather. They'll put me to sleep. Absolutely.
Take some more pizza, guys.